Hello everyone. In this video I'm going to talk about what's in lecture 14, capacitor circuits mainly, and how it works, how capacitors works in a circuit if I connect it to a resistance, understanding time varying current in them, and so on. And we'll touch base on how nervous system actually work as an RC circuit. It's a very cool idea. Overall, what we know before will work here. Q is equal to C delta VC. Again, C here is capacitance. Farad is the unit. Q is the charge. And delta VC is the voltage across the plates of the capacitor, the total voltage across. So I'll say voltage across for short. And U is the electric potential energy. So we can calculate potential energy, knowing charge and potential difference, or knowing capacitance and potential difference. We'll use this version of U. There are other versions, but we can always replace the known values by unknown and resolve. So I'll give you one version of it. One important thing to keep in mind is that capacitors, adding and finding the equivalent capacitance and equivalent in series and parallel circuits are exactly opposite to what resistances do or how resistances works. If I have them in parallel, I just add all the capacitances and that's my equivalent capacitance. If I have them in series, I add their inverse and inverse that's my equivalent capacitance. That's one thing that we might be confused about. Other than that, everything else is the same as the series and parallel resistor circuits. They will have all the same potential differences across if we have parallel arms. Delta V1, delta V2, delta V3 will be equal to each other here, and they will be all equal to epsilon on a plus, not plus, equals. In fact, equating the potential differences and using Q is equal to CV equation, we can prove that the reason why capacitors equivalent capacitance ends up being addition if they're in parallel. We can think of the charge as similar to current. Q totals will be dependent on what capacitance they will have. So we'll call this Q1, Q2, Q3, and when we're asked, we'll find them using this simple equation of Q is equal to C delta V. In the series capacitors, they share the potential differences. They don't have the same potential difference, the total potential differences, or total power source potential. Voltage is shared. Each will have different potential difference if they have different capacitances. And again, we can think of the charge similar to current. We'll have a Q total, and the same charge should be accumulated all on all the capacitors if they are in series. And then when we apply Q is equal to C delta V equation and solve for total potential difference, we will see that it's going to tell us that the equivalent capacitance should be inverse. We don't have to show those, of course. We'll go ahead and use these two equations to solve for equivalent capacitance. Over here we can write epsilon is equal to delta V1 plus delta V2 plus delta V3. Comparing capacitances here, if these are all equal capacitors, just one DC total. Let's see if I call these two C and C, I have them in parallel. So the C equivalent in B will be 2C, in A it's just C, and here I have them in series, and C equivalent in C will be 1 over C plus 1 over C inversed, that will be C over 2. Over here I have a mixed, actually a complex capacitor circuit. These guys are in parallel. I will do their equivalent capacitance first. I'll call the C equivalent 1. It will be 2C. Just add in the capacitances. Then I simplify my system. I replace those two by 1, that is equal to 2C, this guy here, and I have now series capacitor circuit, and I will find equivalent capacitance. It will be CD here as 1 over C plus 1 over 2C to the power minus 1. Let's see what we will have here. Multiply this guy by 2. I'll have 3 over 2C to minus 1, 2C over 3. So clearly this guy has the highest capacitance. Answer is B. We learned about charging and discharging capacitor in a very simple simulation, FAT simulation. We tie our capacitor to a power source, charge it. It's charged here. It will have a total delta VC across. We will call this delta VC0 initial potential difference, initial voltage. It will also have an initial charge Q0. Once we close this, charge will be going from plus to minus, and until this will continue until there is no more excessive charges in either plate. So we'll have all neutral plates and the current will stop. So what we will have, it will have a large initial current I0, and I0 will decrease over the time. So current overall decreases over the time, and after a while it reaches to 0 and there is no more current passing. If we want to plot that over the time, we'll have a graph that looks like this. And this is an inverse power graph, and we can actually define current at any moment in time. Here, for example, what is that current, and so on, using this equation here. I, the current at any moment in time, is equal to initial current times e to the power t over RC. So I is the current at time t, let's say, and I0 is the initial current. And the very same thing happened for potential difference. There was a large potential difference initially, delta VC0, and once we connect our capacitor to a resistance at T0, T is equal to 0, it will start decreasing exponentially. And it has a very similar equation. Delta VC at any moment in time, or at time t, is equal to delta VC 0 times e to the power of minus t over RC. So we can use these equations knowing the initial values. This is initial voltage here, potential difference. We can solve for values at any moment in time. Our Ohm's law still holds. If I'm given initial potential difference, across the capacitor's plates for initial voltage, and if I know what resistance is in the system, I can solve for initial current. And this equation also holds if I know how much charge my capacitor has initially and what is its capacitance. I can find the initial potential difference. And C is capacitance. Charge also changes similarly, but we won't go into too much details of these. Knowing this much will be good enough for us, and we won't be really solving very complicated questions because we won't have time. We need to move on. One important factor here is how fast the current and potential difference is decreasing is called characteristic time, and that's simply what is the value in the exponentials here. So we have e to the power of minus t over rc. This defines how fast we have this decay or change of current, and that's called characteristics time. So if we're asked about what is the characteristic time or time constant, we'll find it using resistance times the capacitor's capacitance. So using the characteristic time or time constant, that letter here is tau, Greek letter tau, we can rewrite the equations of potential difference across at time t or current at time t. And we can define how fast the decrease happens using the characteristic time. At time tau, we have this much change, t is equal to tau. At time t is equal to 2 tau, we'll have this much change. It will be e to the minus 2, because here I'll put t is equal to tau. I'll have e to the minus 1, because that's e to the minus t over tau. That will give me that, and that will give me where I am decreasing. That goes for current as well. Current behaves the same. We can do the same for the charge as well. The following circuits contain capacitors that are charged to 5 volts, so each has the same delta V. Delta V, that will be delta V Z. Delta V is 0, right? So each have the same overall potential difference initially. All the switches are closed at the same time, so we close the switches. After 1 second passed, which capacitor retains the highest charged voltage? So which one has the highest voltage after some time? And we define this by calculating their time constant. Time constant is defined as tau is the symbol R times C. We'll find those. If we have a large time constant, that means my current or potential difference over time decays slowly. That's a long time decay. So if I draw a large one, it will be having a really slow decay, decreases over a long time. If I have a small, this is for a large tau. If I have a small tau or small time constant, then my potential versus time graph will be decaying very fast. So I'll have a faster decay. Everything will finish quicker, and it actually approaches zero. It doesn't become exactly zero, but approaches zero very much earlier than large time constant. So thinking of which capacitor retains the highest charge voltage, I'm looking into which one, after some time, which one has a longer decay time or larger tau. So I'm going to look at their tau values. I'm going to call them tau 1, tau 2, tau 3, calculate them, or tau A, tau B, tau C. Simply R times C. They each start with the same delta VC 0 for all the same. And whoever has the largest decay time or largest time constant will be the one having the highest voltage, because it will decay slowly. The voltage will go to zero slower if it has a larger time constant or characteristic time. For A, what I have is 2 ohms times 1 farad, so 2, sorry, not 1. If I'm using ohms and farad, I'll have seconds. So 2 seconds is the decay time. If I draw the graph, that will be approaching to zero fast. Tau B is RC again. Will be 2 ohms times my C is different here, 0.47 farad, and 0.94 seconds. So decay time is less. After 1 minute, 1 second passes. 1 second. This guy will have more potential difference than that guy, because that guy, less potential difference than that guy, because that guy 0.94 decays faster, has a shorter time constant or characteristic time or decay time, if you like. Going with the similar approach, tau C will be 3 ohms times 1 farad, 3 seconds, the largest so far, and tau D will be 3 ohms times 0.47, smaller. So this guy is the largest decay time. It will have the highest charged voltage.